Last video we developed the rigid body model for rotations and also defined angular acceleration. Now we'd like to tie together those ideas from that video and the previous video where we had developed the idea that torques are somehow involved in causing things to rotate to get a more formal statement of that. So as a working example here towards developing Newton's second law applied to rotation. Okay, technically it's called Newton's second law for rotations, but I like saying applied to a lot of times because it's not a different Newton's second law. As we'll see, it's the same Newton's second law. Anyway, what I'm imagining here is that I've got, just for a working example, and then we can extend this in general, I've got 3 point masses that are connected by massless rods, and we are giving it a counterclockwise angular acceleration just to make things concrete here. So let's go and figure out how each of the masses is going to make their way around. So for the first mass, it's got to be feeling both an inward force and a tangential force. And as a result of those forces, you'll be feeling an inward component of acceleration and a tangential component to the acceleration. So the acceleration is going to look something like this. And then this piece here, or here, let me break it like this. It'll be easier to think about. This piece here will be A1 tangential, and then this piece here will be A1 centripetal. Okay. And then same is true for mass number 2. It's got to be doing something like that. And again, we can break it into pieces. So if this is my A2, this is A2 tangential, this is A2 centripetal, and then finally A3 has got to be doing something similar and breaking it into pieces. There's A3 tangential and A3 centripetal. Okay, now the centripetal accelerations are interesting, but basically all they're telling us is that, yeah, the thing's going around in a circle. And so it'd be more interesting if there'd be some way that we can somehow just focus on the tangential pieces, and that's where we're going to go with this. So let's go look at particle number 1. So for particle 1, we can say that the net force on it would be equal to m1 times a1. And then we can go ahead and take the tangential component of that to say that f1 tangential is equal to m1 a1 tangential. Okay. Now, this x here is my axis of rotation. So this distance r1 would be the distance from the axis of rotation to m1. Likewise r2, r3. So we can use the relation we found last time for the tangential acceleration and observe that f1 tangential has to equal m1 r1 times alpha. And then we remember that as we were intuitively developing our model of torque, one way we could express it was that the torque, due to whatever force is being applied here, right? Because if we have an acceleration, there's got to be some matching force. And this piece here would be F1 tangential. The torque about this axis due to the force being applied here would be equal to F1 tangential times R1. So let's multiply by R1 again. So we'll have R1, F1 tangential equals M1 R1 squared alpha. We say, hey, this bit here now is the torque due to force number 1. And it's equal to M1 R1 squared alpha. Okay, we can repeat this argument for all of the masses, because in order to accelerate mass number 2 around the way we're seeing it, there has to again be a matching force on it with a matching F2 tangential. And here there would have to be a matching F3 with a corresponding F3 tangential. Okay, so, and then for however many particles we have. So we can say that the net torque on the system of particles would be equal to the torque due to force number 1 plus the torque due to force number 2 plus the torque due to force number 3 plus and such for however many particles you have. But we've also worked out that the torque due to particle 1 will also be equal to M1 R1 squared alpha. And then we can do the same thing, M2 R2 squared alpha plus M3 R3 squared alpha, and so forth. And every single one of these terms has an alpha. So let's pull the alpha out. Okay, so we've got a proportionality between our net torque and the angular acceleration of our system. This constant proportionality, if we write this more fancily, we can say this is the sum over all of our particles of the mass of the particle times the square of the distance of the particle from the rotation axis. We'll give this a name and a symbol. The symbol will be I, and we'll call this the moment of inertia for the system. With all of that, we can rewrite this to say that the angular acceleration of a system will be equal to the net torque exerted on it over its moment of inertia. And this is Newton's second law for rotations, or like I prefer to say applied to rotations, because really we just plain started with Newton's second law and just focused on what happened to all the tangential pieces, because that was what we were interested in for thinking about how we could make the thing spin faster or slower. So this is super convenient. It allows us to ignore all of the centripetal components of all of the forces, which are basically just telling us, yeah, the thing's moving in a circle, and that's the force necessary to make that piece of mass move in a circle. Since we know it's moving in a circle, we don't necessarily have to worry about what the forces are. Okay. So the moment of inertia, though, is a little more complicated of a beast. So you may notice an analogy to A equals F net over M here. Now the difference is that with the mass is just the mass. It doesn't change for the system. The moment of inertia, it depends not only on the mass of each of the particles, but where each and every single one of those particles is located relative to the axis you're spinning about. So if you change your rotation axis for an object, you change your moment of inertia. To calculate all but the simplest of these involves the methods of calculus. So, and then usually what people have done is they've used the methods of calculus to figure these out, and then they put them into spiffy little tables. So for instance, let's think about having a long rod as one example. We'll say the rod is of length L and mass capital M. If you are spinning it, thinking about spinning it about an axis that goes through the middle of the rod, the moment of inertia for that rod about that axis has been calculated to be 1/12 the mass of the rod times the square of its length. On the other hand, you can look at that exact same rod and change the axis we're rotating it about to the end. When you do that, people who've done the calculations for these things have shown that the moment of inertia of that same rod about this axis over here is 1/3 ml squared. So for the same torque, it would be you get 4 times less angular acceleration. So an interpretation of the moment of inertia is basically to say how hard it is to twist an object about a particular axis. And this is certainly something you can try for yourself. Take a meter stick or any similar long stick that you can find. Try spinning it about its middle and then try spinning it again, holding it on its end. And you should notice that it feels about 4 times harder to spin it when you hold it at its end. Just to give a few more examples, mostly to show that you do have to pay careful attention to the tables. We could look at a disk, say something like this, radius r. Again, you'll find these in the tables in any book. Again, we'll say mass m. If it's a disk, it will be 1/2 mr squared. If it's a sphere, on the other hand, again rotating about an axis going through its center, like so. The moment of inertia there has been calculated to be 2/5 mr squared. So what we get out of this is that for the same mass, if the average distance a particle is away from the rotation axis is greater, then the corresponding moment of inertia is greater. A sphere is a more compact object than a disk. More the mass is clustered around closer to the rotation axis, and so as a result, the moment of inertia is 2/5. If this were a hollow shell of the same mass, that would be 2/3, which is bigger, which makes sense because as a hollow shell, the matter is on average farther away from the rotation axis. So anyway, these are certainly things that can be looked up in tables whenever you have a need for them. Now, yeah, and in the next series of videos, we will go ahead and take this moment of inertia and use it to find angular accelerations and think about energies. Catch you in the next one.